So now we're going to start talking about what injective means. So a function f from x to y is injective if each point in the range of f is determined by a unique x in the domain x. Each element in y will only have one arrow going to it. Okay, so your domain, they ready, aim, fire, and then every element in the range only has one arrow that they catch. So let's talk about what that means in statement form. I'm going to shorten injective a lot, and then I'm also going to shorten function to funct. So f from x, injective, if the statement, the statement f of x1 equals f of x2 implies that x1 equals x2. That statement is true for all elements x1 and x2 in our domain. So basically what that means is you grab two different elements. You just grab two elements. Maybe they're the same element, maybe they're not, in your domain. And first you check if f of those elements are the same. Okay, so your first element is f of x1, your second element is f of x2. So f of x1, if that does not equal f of x2, boom, statement's true. Okay, if f of x1 does equal f of x2, the only way for the statement to be true is if x1 equals x2, if you grab the same element. Okay, so I hope that's ringing a bell, because if you can think about the negation of the implication, that's the only time that you want, you don't want that to happen. Okay. Another way that you can think about it is the contrapositive. So this is actually the way that makes more sense to me when I first took this class, that if x1 and x2 are different elements, then f of x1 and f of x2 are different elements. So why this makes more sense to me is when I think about injective, I think about an injection. So like if I inject two different elements into f, there'll be two different things. So that's like my weird, that's my weird way that I remembered it when I was younger. Oh, right. So it still is that it has to be true for all. Okay, I just wanted to write the contrapositive, like just that little piece again. Okay, so now let's talk about how you would prove something like this. So you can go about this pretty much any of the ways that you want to. You could do it directly, you could do the contrapositive, you could do contradiction. Whatever's fine. I'm just going to do something direct. So if I look at our first thing here, so f of x1 equals f of x2, because remember, if you're proving an implication thing directly, you assume the if and you show that the then must be true, but that's the only option. So assume, assume f of x1 equals f of x2 for x1, x2, and x. So see, I'm not assuming anything about x1, x2, just that they're in our domain. So everything's good, right? Because this is a function. All right. So since we have this, that implies that negative x1 equals negative x2. So where did I get that? I just got that from the definition. Okay. So what does that mean? Well, where are we? We're in the reals, so I can just multiply both sides by -1. That's okay. We'll still be in the reals. So x1 equals x2. Oh, wait, that's what I want. Boom. Therefore, f injective. Okay, so now let's talk about how we would show that that some function is not injective. Okay, so here we have f goes from r to r, f of x equals absolute value of x, not injective. Okay, so what is the negation of implication? Please, I hope you know this. So the negation of our implication would mean that f of x1 equals f of x2 for some x1, x2, and sorry, I almost said not q, and x1's not equal to x2. So looking at this, can you think of two elements in R that their absolute values are the same, but the elements that you put into the absolute values are not the same? So you probably shouted out plus or minus something, right? So I'm going to start. So first I'm going to start with the definition of injection, okay? Because that's really going to help a lot. I should have done that in the last proof as well. It's always good for you to write down the definition of things because that says to the grader, I know what I'm talking about. And then also it helps you as the writer to bounce ideas because sometimes it's hard to know what to do next or something, or it's hard to remember all the tools that you have, yada, yada, yada. Okay. So this is just the definition of if F was injective. I'm not doing it by contradiction because I'm not assuming that it's injective. You could do that if you'd like. And I just also want to mention this R is the domain. So sometimes you need to be careful about that. If the domain and the codomain are the same, just keeping track of who's who. So I'm just going to say consider plus or minus 1. So I can't just start off by saying f of 1 equals f of negative 1 because I have to explain why. So f of 1 equals absolute value of 1, which equals 1. F of negative 1 looks pretty much the same. Oops. So f of 1 equals f of negative 1, but 1 does not equal negative 1. Therefore, f is not injective. Okay, so I do want to mention, as a side note, this is another way for us to write what the definition of f being injective means. So, but with symbols now. If I want to write the negation of that, I'm going to start with f from x to y, not injective. If there exists, because remember we just switched those two, x1, x2 in our domain, such that in negation of implication is f of x1 equals f of x2, and x1 does not equal x2. Okay, because it may be confusing that I only showed for one thing, okay? So this is why, because all I need to show is that there exists one pair where this happens. And then F is not injective. Throw out the application, it's not going to be injective. Okay, so now let's do another example. I would suggest you try to pause this and try to prove this on your own. So I want to show that F going, so just a reminder, this is the interval from 0 to infinity, not including 0 in the reals. So the assignment rule is that f of x equals the absolute value of x. So I want to show that that is injective. Sorry, this is like blinding me. Okay. Wow, that's spooky, isn't it? Okay, so I want to show that that's injective. So I'm going to start the proof by letting f of x1 equal f of x2. First, just some x1, x2 in the reals plus, because that's equal, then x1, absolute value of x1 equals absolute value of x2. Okay? But since x1 is greater than 0 and x2 is greater than 0, then x1 equals the absolute value of x1. Actually, we could say greater than or equal to. x2 equals absolute value of x2. So that means I'm going to take my line from before and say that x1 equals absolute value of x1 equals absolute value of x2 equals x2. Okay? So then x1 equals x2. All right, therefore F is injective. Oh, excuse me. Okay, so now here, let's show that t going from the polynomials with degree 3 or lower, including 0, to p2 is not injective, where we define that t takes polynomials to their derivative. So I would say try this on your own. Showing that it's not injective, we just need to pick two polynomials that t of those polynomials are equal, but the polynomials themselves are not equal. Okay. All right, so proof. So once again, you're going to want to talk about what injective means if this is on your homework or something. Just for time's sake, I'm not going to keep writing it, as you've seen that I don't keep writing it. But if you're doing this on your homework or on an exam or something, you definitely want to talk about definitions. Definitions oftentimes can give you a lot of points just by stating them. Okay? All right. So I'm going to say consider p of x equals 2 and q of x equals 1. So there's actually a lot of polynomials you could choose from, as long as they're in the domain. All right, so now let's talk about t of p with variables in x is p prime of x, which is 0. Similarly, tq with variables in x is the derivative of q, which is also 0. So, because the derivative of a constant is 0. So, t of p equals tq, but p is not equal to q. Therefore, t is not injective. We're going to talk about surjective. So, a function f from x to y is surjective if for all elements in y, in its codomain, there exists an element in its domain that hits it. Okay? So what you want to be imagining here with our two little circles, for every element in y, there is an x that hits it. Okay? So every element is catching an arrow. But it might be catching multiple arrows, okay? Which, from last video, you know would mean it's not injective. So surjective and injective don't necessarily affect each other. So if we're trying to show, it's not surjective, we only need to show there exists some y in our codomain such that for all elements in our domain, f of x is not equal y, or f to not be surjective. Now let's do a couple of examples, and if you want to try these on your own, I by all means, I would love that. I would love for you to try every single thing I show you on your own first. And please do not give up quickly on yourself. This stuff is difficult, and it might take a few times to look at it and to try it for it to really start processing. And also remember that there's a bunch of different ways to do it correctly. Okay, I'm not showing the only way to do it correctly. All right, so let's show that this function is surjective. All right, so what are we going to want to do? So we want to show for all y for all elements in our codomain that there's an element in our domain that hits it. So here's the general setup for me. Is I think about, well, let's just choose some element in our codomain, okay? Because I want to show that if I choose any element in my codomain, I'm going to be able to do this. I'm going to be able to find at least one element in our domain that hits it, okay? So let me just choose a generic, like just, close my eyes, put my hand in the bowl and pick out an element. Some element y in R+. And then you can write, and this would mostly be for yourself, is to say codomain. But it's also a nice note to the grader that, like, you know what you're talking about. You're not accidentally picking something from the domain. It just speaks that you know what you're doing.
Now let me introduce another tool you can use inside of proofs. It's called
scratch work. Okay, so that means you're working through something, you're trying to demonstrate your knowledge, but maybe at the beginning of the scratch work, you're assuming something that you're not allowed to in your proof. Okay, so basically what it is you get like this playground of where you get to assume things that you wouldn't normally be able to, but it's all for the sake of trying to find out more information. Okay, so let me demonstrate what I'm talking about. So in this one might be a little bit simple, so you might think I'm a bit ridiculous for doing this, but like I said many times before, I want to demonstrate these things when they're a little bit more simpler so that you can really get a grasp on them before they get more complex. So I have some y, right? So I want some f of x to equal y, x being in the real plus, okay? So why I'm allowed to assume this is because I'm just in scratch, okay? If you just start writing this in your proof, you're going to lose a lot of points because you're not allowed to just assume that. But watch what's going to happen. So f of x equals absolute value of x equals y. So now I know, so the x that I'm looking for, its absolute value must be y. So x could be plus or minus y. I can't choose x to be negative y because y is from the positive, so y is positive, and then x needs to be positive. So that means that x cannot be the negative of y because the negative of positive is negative. So if y was negative for some reason, then yeah,
you would have x equal negative y.
Greater than 0, maybe you write that, so x equals y. Okay, and so I always like to section it off. You can make it into a dream cloud or something, but I like to let the grader know where I'm starting and where I'm ending. Okay, and so it was just for the sake of figuring out what it is I'm trying to do. So I'm considering some, or choose, maybe I'll say choose some y in the reals, in our codomain. Consider f of y. Okay, because from my scratch, I'm taking my information over here because all I have to do now is go backwards, go back to where I started, and then I get exactly what it was that I wanted. Okay, so now because of my scratch, I know I'm going to say, okay, f of y. So consider f of y. And y is in the codomain, so it's in the domain. It's complicated, right? It's just because they're equal. Okay, so f of y equals absolute value of y. Since y is greater than 0, then absolute value of y equals y. So, whoops, f of y equals y. Bada bing, bada boom. Therefore, f is surjective. And remember, you want to be saying what the definition of surjective is. And I would say typically you would write it in the beginning or you'd write it at the end. I'm just not going to write it just for time's sake. Okay, so for this proof, all we need to do is find one element in our codomain, which is the reals, and show that it doesn't get hit. Okay, so something that you might notice is f just sends the integers to the integers. So it hits every single integer. So if its codomain was the integers, it would be surjective. Okay, so we just need to pick something that's not an integer. Let's say 1/2. Okay, I thought of a better way to do this. All right, since x is in the integers, then negative x is in the integers. Okay, that's what we were talking about before. Therefore, f of x is in the integers for all x in the integers. Okay, so now we've defined our range, right? But we still need to go one step further and just explain why the integers and the reals are not equal, which may sound silly, but you want to be thorough. Consider 1/2 is in the reals minus the integers. Then there exists no x in the integers such that f of x equals 1/2, since 1/2 is not in the integers. There's a bunch of different ways you could do this. I just like this one. Therefore, f not surjective. Okay, and so maybe down here is where you could write the definition of surjective. This was like a homework or an exam or something. Because you want to demonstrate that you know the definition of it. You definitely want to do that. Okay, now here's a fun one. So we're going from P3 to P2, and what T does is it takes a polynomial and it takes the derivative of it. So now I want to show that that's surjective. So I would suggest try it on your own. Like, just try it. And if it starts going nowhere, read over it again, or start it new or something. Maybe sleep on it and watch this video tomorrow. I don't know, but this is a really cool one. All right. So I'm going to do it like I did before. I just choose some element in our codomain. So choose, let's say, P of x in P2. So if we remember, now P of x, its degree is either less than or equal to 2, or it's the 0 polynomial. Okay? But in general, we have a way of writing that. Then there exists some a, b, and c in the reals such that P of x equals ax squared plus bx plus c. So maybe they're all 0. Maybe a is 0 and b is 2 and c is -10 or something, you know, I don't know. But that's our whole generality thing, right? We don't want to fix something particular. We want to be able to consider any element in P2. So now let's move over to Scratch. I want some q, let's say, that equals P of x. Okay, so for q in P3. All right, so what does that mean? That means that q prime of x equals P of x. But now I have this different way of talking about P of x. Because right now this just kind of looks like gibberish, right? Who's P, who's Q? I don't know. So I want ax squared plus bx plus c. Okay? So that's the derivative of q of x. Interesting. So q of x, we can use alpha x cubed plus beta x squared plus gamma x plus delta. Okay, these are Greek letters. All right, so if I take the derivative of this, it needs to be equal to this guy over here. So this needs to equal ax squared plus bx plus. So if these two things are equal, that means that gamma equals c, that 2 beta equals b, and 3 alpha equals a. I hope that's making some sense, because 2 beta can't contribute an x, and now we're x squared, so it has something to do with ax squared. No, that's not possible. Okay, so we have this. So since I'm going to be writing what q of x is, I'm trying to figure out who q of x is, why don't I write it in terms of gamma, beta, and alpha? So this one would stay the same. This one I can change it to beta equals b over 2. And then here I can say alpha equals a over 3. So here's my magic ticket. And now delta, I'm like, who the heck's delta then? Make it 0, make it 1, make it a gajillion, Jeff Bezos net worth, it doesn't matter. As long as it's a real number. Okay. Consider q of x equals, so let's look back. Okay, so q of x, we're going to have a over 3x cubed plus b over 2x squared plus gamma x, and I'll just have delta be 0. So consider that. And so sometimes when it's like really treacherous computations, you can say by scratch work, blah, blah, blah. Okay, you can't say by scratch work, I'm done. But you could say by scratch work, like T of Q equals P. But this is not very treacherous, so we should just do it. That's what I'm using, right? T? Yes. Okay, cool. All right, so T of Q with variable x equals Q prime of x, which is ax squared plus bx plus gamma. Oh my gosh, I still wrote gamma. Cx plus c. Okay? So, but this equals p of x. Woohoo! Therefore, by definition, T is surjective.